Hey, so now we're done with finding the probability of a normal distribution, and that was all fun and dandy, but what can we do with the normal distribution? Like, so what? Not everything is going to be normally distributed, so what do we do with all this information? Well, that's what this is going to be about. All right, so some reminders of things that we've talked about before we move on. So we have a population. The population is a set of all measurements under consideration. So imagine we want to know the amount of salt in the entire ocean, right? The ocean would be the population, right? And we want all the salt from that. But that's impossible to do. We can't just boil down the water in the ocean, all of it, and see how much salt's there. That would be ridiculous. So what do they do when you Google? Where did they get that number when you Google and say, go like, hey, what is the salt content? They'll give you a number on Google. But what do? They take a sample. A sample is a subset of measurements from a population, right? So we take a sample of the water, we boil that down, and we see what it's going to be. Right? That's our sample. Of course, we can't just take one sample. We got to take lots of samples. And so we take lots of samples and we see what happens, right? So that's what we're going to do. And what we're going to see with that is that we can make inferences about a population parameter based on those statistics. So that means we can make judgments, right? We can figure out what's going on in our population based on our sample. And that's where statistics gets really, really powerful. So what we're going to do in this video is we're going to talk about the sampling distribution of the sample mean. Basically, if we take the same bottle and take samples and samples and samples and samples and over of the same amount of the ocean water, and we see how much salt is in it, basically all those means would equal the population mean. That's what's awesome about this video. Okay, so what we're going to see and what I want you to think of as we go through this video is a sample mean targets the value of our population mean. The sample means, all those jars put together, will target the value of the population mean, which means it's going to be the same. We're also going to see that the distribution of the sample means tend to be normally distributed. That's exciting, right? Because if it's a normal distribution, think back of what we just got finished doing. We can find probability. And that's the exciting part about it. So no matter what our population looks like, we're going to find out if we can find the probability of any distribution, even if it's not normal. Okay, so here we go. One semester I had a small stats class of 5 students. I asked them the age of their cars and obtained the following data, and here it is. So assume this is like Richard, Karen, Oscar, Tess, and George. So these are their names and these are the ages of their cars. First thing we want to know is, what is the population mean? So from way back, that we know the population mean is mu. So we want to find what mu equals. So I'm going to put this data into StatCrunch. So here we go. Just putting it right here. These are going to be my ages. 2, 4, 6, 8, and 3. Just make sure I get those numbers. 2, 4, 6, 8, 3. Perfect. There they are. To find the mean, we go to Stat, Summary Stats, Columns. I'm going to find my mean, and that's all I need. It's just my mean. And we know from way back when, this will give us population mean or sample mean. We click Compute, and we get 4.6. 4.6 is our mean. So here we go. Back to this. Our mean is 4.6. Now, what does this have to do with the sampling distribution? Imagine instead of such a small population, I was looking at every student in the entire world. Well, there's no way to get their ages of their cars, which no way. So what I'm going to do is, if I had a huge population, is I'd take a few samples, right, over and over and over, and take lots and lots and lots and lots and lots of samples. So that's what I'm going to do here. Instead of looking at, again, I know it's a small population, but let's assume it's huge. I'm going to take samples, let's say, of size 2. So that means I'm going to take 2 people at random, but I want to know all of them. All the samples of size 2 I can possibly get. So for example, I could take Richard twice, right? His age of his car is 2 and 2. Just by random, I could get him twice. Put him in the bucket and then take him out and put him back in. Yep, I could get him twice. I could get Richard and Karen, so ages 2 and 4. I could get Richard and Oscar, 2 and 6. I could get Richard and George, 2 and 3. Is that all the ways I can get 2 people by random? No. Oh, I forgot Richard and Tess, 2 and 8. No, I could get Karen first, right? I could just happen to get Karen. I could get Karen and then Richard. I could get Karen twice. I could get Karen and Oscar. I could get Karen and Tess. And I could get Karen and George. Is that all? No! I could get Oscar and Richard. Oscar and Karen. Well, you can see. I can get lots of different ways, right? And so those would all be samples of size 2. So n, lowercase n is 2. And what I want to do is find the sample mean, because remember that I said the sample means should target the population mean, and our target is 4.6. So I'm going to find the sample means. So each x bar. So 2 plus 2 is 4. 4 divided by 2 is 2. 2 plus 4 is 6. 6 divided by 2 is 3. 2 plus 6 is 12. 12 divided by 2 is 6. 2 plus 3 is 5. 5 divided by 2 is 2.5. 2 plus 8 is 10. 10 divided by 2 is 5. And I'm just going to keep on doing that over and over. Luckily for you in this video, so in the essence of time, I did this already. And there it is. So here's all of them. And notice there's going to be 25. There's 25 of them. And I did that for you. And we have each of the x bars. So again, 2 plus 2 divided by 2. 2 plus 2 is 4. 4 divided by 2 is 2. So that's where I got that. I did that for each one. So for example, 4 plus 3 divided by 2. 4 plus 3 is 7. 7 divided by 2 is 3.5. Okay. So what do I want to do with that? Well, I want to find the mean of each of the 25 samples. Then, once we do that, we're going to compare our population mean, which we know is 4.6, and the mean of our sample mean. So the mean of all those sample means, all 25 sample means, the mean of those. And then we're going to see if it actually targets. And remember what I said target meant. It is the same. Okay, so let's find the mean of all 25 of these. So I happen to put all 5 of these into StatCrunch, and that's what this column was in case you were looking. So I did that already. There's 25 of them, and I go to Stats, Summary Stats, and Columns. I choose my column. I just want my mean, the mean, there we go, because I know that is population or sample. And are you ready for this? I mean, I don't know if you're ready for this, because this is exciting. It's very exciting. Take a deep breath. Are you ready? Click. Compute. Oh my goodness. What have we just found out? We have just found out that our sample means, all those means of the sample means is 4.6, and our population is 4.6. So, looking at that, the sample means, all of those were 4.6. We know the population mean was 4.6. The mean of the sample means is 4.6. So does it target it? Yes. Yay, stats. It does. Isn't that amazing? With all that chaos, all those numbers, it made the same mean. So what can we do this? What can we do with this? All right. So I already did that. Okay. I can make a dot plot. So this is my first sample, 2, 3, 4, 6, 8. Now the problem with StatCrunch is, if you look up here, it says up to 3 values per dot. So we know n equals 2 should have 25 dots, but they've been kind of congealed in. Now I was bored, there's only 25, so I did this also with sample size 3 and sample size 4, and you can see how many dots we have. So looking at this dot plot, I want to know for samples of size 2, so this one, what is the probability that it is exactly 4.6? So here, approximately is 4.6, and so looking at my dot plot, I don't think any of them were 4.6 exactly. So let's look back and just make sure, and look through here to see if any were 4.6 exactly. Well, I have 4.5, but that is not 4.6. In fact, none of them were 4.6. And so let me go on. So that would be 0 out of 25 because there were 25 x bars. So 0. Okay, so no individual sample will probably be just like our population sample. So think of it as that ocean water, right? There's no way that one little jar is going to be the same salt content as the entire ocean. So instead of looking at just one individual, let's look at a group. So what is All right, so now we want to find for samples of size 2, what is the probability that it will be within 1 year of the population mean? So I know my population mean was 4.6, so within 1 year, if I subtract 1 year, that would be 3.6. If I add 1 year, that would be 5.6. So 3.6 to around 5.6. And again, if I had all the dots, all 25, I could just count the dots. However, I can't count the dots, so I'm going to go back to my raw data. And again, I'm going to do previous. Keep on losing my pen. All right, so between 3.6 and 5.6. So that's not between that. That's not. That is. That is. That is not. That's not. That is. That is. That's too big. That's too small. That is. That is. That's too big. That's too big. That's good. That's good. Too big, too big, too big. That's good. Too small, too small. That's good. That's good. Too small. All right, so all I did was see if they were between 3.6 and 5.6, and if I do, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of the 25. So that would be 11 out of 25, and I get my handy-dandy calculator. 11 divided by 25, and I get 0.44. So almost half of them are within 1 year of the mean, right? 1 year of the population mean of 4.6. So it's not ever going to be exactly 4.6, very unlikely. However, I could find the probability of any one time. So for example, 2, having a sample size of 2, that's only 2 happens one time out of the 25. If I look at my next age of 2.5, 2.5 happens twice out of 25. So that's where this came from. 1 out of 25, 2 out of 25, I could keep going. So if I did it this way, if I want to know the probability of within 1 year, of 4.6, which we know is 3.6 to 5.6. I could just look between 4 and 5.5. 3 plus 2 is 5, plus 4 is 9. 9 plus 2 is 11 out of 25. So just different ways of finding that same probability. All right, so let's see what else happens. Now, if I look at this data, again, n equals 1, that's my raw data. It's going to be just a straight line, nothing repeats. N equals 2, we do have some repetitions. N equals 3, let's see what happens. That's interesting. Remember 4.6 is around here. Ooh, that's bad. But if we look at n equals 4, right? Oh my goodness. Look at that. What is this? What is this curve? It is our bell shape. Oh my goodness. It is our normal distribution. So it kind of starts growing and starting to look at our normal distribution. And notice that most of our data is right around 4.6, right? That's the normal distribution. Like it's all clumped together. And it definitely clumps together the closer we get to a larger sample. In fact, no matter what sample size we take, our mean will always be 4.6. So this is our original data, so this would be mu. And this is our sample size of 2, the one that we just did. And again, I got bored and oh my goodness, do you see how many I did on this one? Oh my gosh. But I did it right because I knew that the sample mean should be 4.6, right? It's 4.6. So no matter what our sample size is, all those sample means will always be 4.6. The standard deviation though, right? The standard deviation changes. This is sigma, right? That's our population. But we said that as we look at those normal distributions, we get more and more values in the middle, right? So that is our standard deviation. So notice our standard deviation will get smaller and smaller the larger our sample size gets. Okay, so what I want you to get out of this, besides how to take samples, is that our sample means will cluster closer around the population mean as our sample size increases. So think of those dot plots that we just saw. At n equals 4, there were a lot more dots around 4.6. And of course, the larger the sample size, the smaller the standard deviation of all those sample means. All right, and that is it. I'll check you on the next video.